Hi, thanks everyone for being here this morning. It's my pleasure to introduce Bryan Robinson, who is the assistant lead of the Optical Comm Tech Group at the MIT Lincoln Lab. Bryan is the lead systems engineer for the Lunar Laser Communications demonstration mission. He helped architect the Lasercom system, oversaw development of the space and ground terminals, and led the systems operations for NASA's first successful demonstration of a high-rate Lasercom system for space. Today, he's leading a variety of follow-on efforts to develop enabling laser communication capabilities for future near-Earth and deep space missions. So please join me and thank Bryan.
Okay, can everyone hear me? Thanks for that introduction. So today I'm going to be talking about optical communication flight systems, and the intent here is to go from the concepts about optical comm that were discussed in the prior talk to actually looking at what this means in terms of implementation and some of the hardware that's been built and demonstrated to date. And by way of introduction, I'd just like to point out that really in the last 15 years, there's been many successful optical comm demonstrations, and this is probably not everything, so if you don't see your project, I apologize. But the point here is that optical comm has been demonstrated successfully in many different domains: space to air, air to space, space to space, LEO, GEO, the moon. It's been demonstrated by many different nations: the US, France, Germany, Japan, China. Many different organizations have engineered and operated these systems as demonstrations. And in fact, today it's becoming operational. And so I'm going to tell you a little bit about the hardware, trying to focus on the space side, but also touching a little bit on the ground side for these systems. And the outline of my talk is shown here. First, I'm going to talk about near-Earth Lasercom systems. And here I have to offer a little bit of an apology. Originally, I coordinated this presentation with Frank Heine at TESAT, who was planning to be here, but at the last minute had to cancel his trip. And so I've got a few charts from Frank that I will share with you and do my best to brief, but really that was his domain to speak to, so I'll do my best there. And then I'll talk about deep space Lasercom systems and how those look and how they might differ from the near-Earth Lasercom systems that have been demonstrated. So first, as I mentioned, Lasercom today is becoming an operational reality, and in fact, the European Space Agency has sent up the initial nodes for its European data relay system, and this is an optical communications system where data from low Earth orbiting spacecraft are relayed to a geosynchronous spacecraft via an optical link, and then the geosynchronous spacecraft sends that down to the ground with a radio frequency Ka band link. And this system is in operation today. In fact, there are now 2 geosynchronous nodes that are in operation, and 3 low Earth orbiting user terminals that are also being used as part of the system. And so there's a total of 5 operational optical terminals that are being used today for that. And here's an image of what the space terminal looks like. And so this is a high rate link. It operates at about 1.8 gigabit per second user data rates, and accounting for the bandwidth expansion that you get from the coding, that's about 2.8 gigabit per second optical data rate. The system is homodyne BPSK, so it is phase shift modulated. I'll say a few words about that in a moment. It operates at 1 micron wavelength and relies on a low line width laser that's been developed by TESAT for these types of applications. It has a beaconless spatial acquisition where the 2 terminals can find each other by doing a scan and acquiring the signal, and that can happen very quickly, typically on the order of seconds. And you can see here the dimensions of the terminal. It's sort of about this big and weighs about 50 kilograms and operates at about 160 watts. One of the interesting aspects of how the system was architected is that both the LEO user terminal, shown here in this photograph, and the GEO terminal are designed to be identical. And this was a decision made for really manufacturability reasons, so that they can set up a manufacturing line for building these terminals. And as I mentioned earlier, they are building many of these terminals. And the LEO and GEO terminals look the same. And there you can see a photograph of 2 of them side by side. And as I mentioned, at the heart of the system, this is a coherent detection of binary phase shift keying. And so the way this works is that at your receiver, you have a local oscillator that's matched in frequency and phase to the transmitted laser. And this is done in the optical domain. You mix those 2 signals together onto a detector, and the photocurrent that's generated in the detector is proportional to these terms There are power terms related to the carrier and the local oscillator. And then this term is the one that is actually the modulation that's detected. And so here you can see that there's a term proportional to the phase difference between the local oscillator and the transmitted carrier. And by measuring that term now at baseband, you can determine the phase modulation on the signal. And so this is a very efficient form of modulation. It does have some complexity in that you have to be able to track the phase of the incoming carrier with your local oscillator. But as I mentioned, this is an operational system today, and so those problems have been solved and done very efficiently. And here you can actually see an example of the dynamic range that the system has. And so it can operate over a 40 dB dynamic range in power and do that very efficiently. So coherent systems are very efficient. This is what's done in the radio frequency domain, and today this is what's being used for this operational system near Earth. Now I'd like to transition from there to talking about deep space systems and some of the challenges that exist there and how those have been solved. And so to do that, I just show here a plot on a logarithmic scale of the ranges of places where you might want to communicate in the universe close to us, going out to Pluto. And data rate here on the y-axis. And so if you have a system operating at a gigabit per second at geosynchronous orbit, like that system from TESAT and the European Space Agency, just because of the power law loss, as you go further out into the solar system, this is how much power you can deliver, and corresponding, this is how much data rate could be supported if you keep everything in the system the same, the apertures and the transmit powers. And so this means that gigabit per second system at GEO does 10 megabits per second at the moon, and going out to Mars, you're at 10 bits per second. And so that by itself is not very useful. And so as you go to deep space, you got to think about how do you do better. And so I mentioned the Lunar Lasercom demonstration. This was operated back in 2013 and 14, where we demonstrated 600 megabits per second from the moon. And the prior speaker mentioned that there's also a deep space optical comm development here at JPL, where they're working on systems to operate at Mars or somewhere between here and Mars. And right now that's planned to operate at sort of 100 megabits per second down to a few hundred kilobits per second. And so what I want to talk about is how do we engineer these systems to get off of this curve at near Earth and to operate at deep space. And really what's behind it all is the link equation. This was also shown by the previous speaker. My terms are a little bit different here, but basically the received power is related to the power that's transmitted times the losses in the transmitter times the transmit antenna gain, which you can see has this lambda squared in the denominator, which means that the beam can be very directed for optical wavelengths. Then there's the range loss. This is the r squared loss. As you go further out, the power goes down by the square of the distance. And then at the ground terminal, you have a collector that's characterized by a collection area and then its own losses to give you the total received power. And then to translate from power to data rate, you take that power, you can divide by the photon energy to get photons per second, and then the efficiency here denoted by eta, which is how many photons per bit does your receiver need to operate, and that gives you a data rate. And so I'm going to talk about a couple different aspects of this equation in terms of how they relate to the engineering of the space side. And I'll first start talking about the space terminal aperture gain, which was already mentioned previously. And as an example, since this is what I'm most familiar with, I'll talk about LLCD. Again, this was a NASA demo that was operated on the Lunar Atmosphere and Dust Environment Explorer spacecraft that demonstrated a 622 megabit per second downlink from the moon and a 20 megabit per second uplink to the moon. And this is what the terminal looked like. There are three modules that were mounted on the LADEE spacecraft. On the exterior is the optical module, which was the telescope that was used to direct the beam toward the Earth. Inside, there's the modem. This is the box that basically transmits the bits of information you want to send to the photons that need to go to the Earth, and it's fiber coupled to the telescope. And then there's a controller that controls all of the beam pointing functions of the telescope. The LADEE spacecraft was a small spacecraft. It was a couple hundred kilograms. The space terminal mass in this case was about 30 kilograms, and the operating power is about 90 watts. And so first talking about the aperture, so as I mentioned, there's this term for aperture gain in the link equation. I've plotted it here at a wavelength of 1550 nanometers as a function of the aperture diameter. And you can see that there's very, very large aperture gains that are possible for fairly small apertures. But on the other side, as you make those apertures bigger, the beam gets narrower. And so this is the beam width in microradians plotted as a function of that aperture diameter. And so as an example, that LLCD system had a 10 centimeter transmit aperture which gives you 106 dB of link gain in your link equation, but you've got a 15 microradian beam width that you've got to point. And so 15 microradians is about 1/1000th of a degree. And I'll show you what that means in a second. It's a very, very tiny beam. It's hard to visualize, actually. The deep space optical comm terminal that was already mentioned has a somewhat larger aperture designed for operating at larger ranges, about 22 centimeters, which corresponds to 113 dB of gain, but an even narrower beam of 7 microradians. And so let's just consider for a moment what a beam looks like at 15 microradians. So this is an example of what the beam from the moon looks like from a 10 centimeter 4-inch aperture, which produces this 15 microradian beam, 0.001 degrees. And so this is a Google Earth image of White Sands, New Mexico. Here's the ground terminal that was used for the Lunar Lasercom demo, installed there at that NASA facility. And overlaying that with the beam width, the beam fills the field of view. So it looks pretty big on this scale. But if we step back by about a factor of 10, you can see here the beam is about 6 kilometers across on the Earth coming from the moon. Step back a little bit more. Here's New Mexico and Texas, and you can see right there I can't even stabilize my laser pointer, but that very, very small dot is the beam, and one more step, and there it is from the moon. And so it's a very, very small beam, and it is hard to visualize, but the moon, the Earth as viewed from the moon is about 2 degrees wide, and this beam is 1/1000th of a degree. So you got to point this beam to 1/2000th of the Earth diameter as seen from the moon. And so this is a challenging engineering problem, and the challenge lies in the fact that there's many, many different disturbances on the spacecraft that affect you. And so this is sort of, in the general terms, looking at frequency and the types of disturbances that you see. And so out at high frequencies, the platform that you're on is vibrating. There might be solar panels that are moving. There are reaction wheels that are spinning. Those vibrations, in fact, can be much larger than these 1,000th of a degree beam widths that we care about. At lower frequencies, you got to deal with the fact that the spacecraft might be changing position and orientation. The target might be moving depending on what you're talking to. And at lower frequencies, you have to deal with terminal distortions and the fact that as temperatures change, when you come in and out of the sun, things might twist and turn in ways that misdirect your beam. And so this figure at the top sort of shows a typical optical comm system as they're typically implemented, where you've got a transmitter and a receiver. And I'll say the traditional approach to dealing with these systems has been to the degree that you can, you isolate from the platform vibrations by putting vibration isolation between the platform and your terminal. And then you rely on optical tracking of the other end of the link to reject all of the lower frequency. And I'll call this high bandwidth optical tracking. And this is sort of what's done in that EDRS system. Now, when we think about these deep space systems, there's a bit of a challenge with this approach in that, again, this is the power loss that you get as you go further out. So if I start at say, 1 here and go out, I lose power like this. Turns out that the bandwidth that you can track with goes down even steeper. And so now if this acts as bandwidth of my tracking system, it goes down like r to the 4th. And so very quickly, if you're relying on an all-optical tracking system like this, it's hard to deliver sufficient power. And so what this says is that if I want to have an equivalent tracking system at the moon, I've got to deliver 100 times more, either in power or aperture, in order to track with the same bandwidth. Or if you go out to Mars, we're talking about 100 million times more power or aperture, which quickly becomes very, very challenging. And so as a consequence, when you engineer these systems for deep space, high bandwidth optical tracking with a beacon doesn't really work as you go further out. And so we rely on other sources like celestial sources. I can see stars that I can use to do some low bandwidth tracking. I can also use inertial references where I put, for instance, an inertial reference on my telescope platform, and I can measure the disturbances and actively reject them. And so when you do that, then you can lower the bandwidth that you need for your optical tracking. And so the approach we used on LLCD was a combination of this low bandwidth tracking together with inertial references. And in terms of what it looked like, you can see here in this diagram an exploded view of the optical module that we had. The telescope was mounted on a 2-axis gimbal that allowed us to offset point from the bus. And the telescope itself had inertial sensors on it that then rejected vibrations from the spacecraft via voice coils that were used to attach it to the 2-axis gimbal. And then in the back end of the telescope, you can see here we focus down into a smaller beam, and there's really 3 paths that we rely on. So the transmit beam originates in this fiber, bounces off a dichroic, and then goes out. The receive beam comes in, one wavelength passes straight to the receive fiber, a second wavelength goes to a wide field of view acquisition sensor. And this is used during initial pointing to find the ground terminal. Both of these fibers are mounted on piezo actuators, which allows us to vary their relative position. And in fact, the transmit actuator allows us to vary the point ahead. So in an optical system, the beams are so narrow that where you actually see the other end of the link is where it was when it transmitted the signal, but that's not where it is now, and that's not where it's going to be when your photons get there. And so you have to have offset pointing between the transmitter and the receiver. The receiver had a piezo actuator that we varied in order to track on the signal directly coupled into the fiber. And so that's sort of what this system looks like when you look inside it. The other thing I want to talk about a little bit for deep space systems is this idea of efficiency. And there's different ways that you can modulate and detect signals to improve your efficiency as you go to deep space. And so to do that, I'll just start with a couple equations which we don't have to understand in detail, but you'll have them here for reference. So when we talk about efficiency, a good place to start is channel capacity. And channel capacity is something that was defined by Claude Shannon back in the 1940s. And it basically represents the maximum data rate that you can support on a channel, in this case, a band-limited additive white Gaussian noise channel. And so you can see that the capacity here is expressed in terms of the bandwidth of the channel, the power going into your receiver, and the variance in the power that comes from the various noise sources in the signal. And what Shannon showed is that for reliable data transfer, the data rate that you operate at has to be less than this capacity. And so if we express this data rate here as R, you can rewrite this equation in a way that talks about the fact that the signal-to-noise ratio, the energy per bit divided by this noise variance, has to be greater than this expression. And here, we call this the power efficiency, and this data rate divided by the bandwidth is really the bandwidth efficiency. And so for radio frequency links, this is of great concern since you're typically very bandwidth constrained by regulations and such. And so you typically want to maximize your bandwidth efficiency, and perhaps you're willing to pay power to do that. And so if you plot this curve, it looks like this. And what Shannon's capacity tells us is that in the regions above this curve, you can't operate error-free. And in the regions below this curve, you can operate error-free. For optical systems, oftentimes I like to plot the curve this way. And here I've switched the axis a little bit because in an optical system, we've got lots and lots of spectrum available. So typically, spectrum is not a constraint, although there may be other bandwidth constraints in the system. And so instead, what I plot here is the power efficiency that you can achieve as a function of the bandwidth expansion. And so this is how much bandwidth do I use for each bit per second of data rate that I support. And so as I use more and more bandwidth, I can make my system more and more efficient down to about minus 1.6 dB SNR for these types of systems. And it turns out that homodyne system that I talked about before exactly follows this curve. And in this case, for optical systems, the signal-to-noise ratio is a function of the number of photons per bit that you receive, because typically optical systems that are well-designed are dominated by the shot noise of the incoming signal as opposed to other thermal noise sources that might exist. And so instead, I can express this efficiency in terms of photons per bit, and this is what it looks like for that homodyne system that I showed you. And so for homodyne systems, this is as well as you can do. And I'll also point out that today, and in fact the last couple of decades, this has really been developed, that there are coding and modulation techniques that can get you very close to this curve. And so this is a good curve to use when we analyze systems because we actually know how to implement systems that can get close to that curve. So now I'd like to tell you about, in optical systems, there's a way that you can even do better than that curve. And there are numerous ways to do this. The example that I'll give that's commonly used is to use a modulation format called pulse position modulation. And with pulse position modulation, it's an intensity modulation, and what we do is we group bits together to be sent, in this case 4 bits at a time. That generates a symbol that ranges from 0 to 15. And then we transmit that symbol by selecting a pulse. Out of 16 possible slots, we put a single pulse in the slot corresponding to the symbol for those 4 bits of information. And so now in the absence of background, all I have to do is detect a single photon and determine which of these 16 slots it was in, and I can recover those 4 bits of information. And these photons can be detected with Poisson statistics, and so the single photon detector detection probability is given by this equation, and it's basically an exponential in terms of the power received M is the PPM order, which in this case is 16, divided by the photon energy, and W in this case is the number of slots per second that I'm transmitting. And so that's the detection probability. And if you calculate the capacity for this channel, it's a very simple expression. It turns out that the capacity is simply given by the symbol rate, which is the slot rate divided by M, times this detection probability, times the number of bits per second, number of bits per symbol, which is log 2 of M. And so this is the capacity formula. Again, I can rewrite that in terms of a photon efficiency that I define in terms of the received power, the photon energy, and the data rate, and a bandwidth expansion, which I define in terms of the slot rate divided by the data rate. And now you find that this photon efficiency has to be larger than this term here. And you can optimize that term for a given bandwidth expansion. You can optimize over M. And what you find is that now the capacity curve looks like this red curve. And you can see that with enough bandwidth expansion, I can actually do better than what the homodyne system can do. And so typically what's done today is that the coherent receivers, like the EDRS system, those have very good efficiency. They operate on this blue curve. They can be done very wide bandwidth at very high data rates. They operate with a single spatiotemporal mode, which has advantages and disadvantages, but that's the nature of the system. So they're often used for systems that are high data rate, systems that are near Earth where you can deliver sufficient power to support those high data rates, and they're often used for space-to-space systems where this coupling to a single mode is practical. For deep space systems, we often use photon counting systems like what I just described. These also have very good efficiency, especially if you can get the bandwidth expansion high. Typically, these systems do have other bandwidth constraints. There's not a constraint on the optical spectrum that you use, but there are other constraints in terms of implementation and the bandwidth that you might have in your electronics that are generating the modulation, or the timing resolution you have with your detector on the ground. They can be multi-mode, which is useful for links going through the atmosphere where it's hard to couple to a single mode. And so as a consequence, these systems are typically used for lower data rate, maybe up to gigabit per second type rates. Deep space type links are often in this category, and links that go through the atmosphere where a multi-mode receiver might be useful. And so just a few words on how we implement this. So pulse position modulation, oftentimes you implement in what we call a master oscillator power amplifier type of a situation. And so you have a source laser that goes into an intensity modulator that you turn on and off that laser with the encoded pulse position modulation data. And here you can see a few examples for binary pulse position modulation, 4-ary and 8-ary. If you just did this, this wouldn't really be very useful, because what happens is that the average power that you transmit is going down as I increase M. And so that's not particularly useful. You get more efficiency by going to higher M, but if I lose average because my peak power is limited, that's not very useful for the link. And so then what we do is we go into an average power amplifier, and an example of such an amplifier is an erbium-doped fiber amplifier that's useful at the telecom wavelengths of 1550 nanometers. And we can amplify that power up to about half a watt to maybe around 10 watts with existing technology today. And what's interesting about this amplifier is that it's average power limit. And so at the output, in the way these are operated, the average power is fixed. And so for different M's, that means that the peak power gets higher as M gets larger. And so that's what we've done on LLCD. That's what other systems for deep space have done. Here's a photo of the Lunar Lasercom modem that was developed that operated at rates from 40 megabits per second to over 600 megabits per second. We used a half-rate forward error correction code for this system. It was fixed for 16-ary pulse position modulation, and we had a half-watt erbium-doped fiber amplifier that was used to transmit the signal. On the ground, the other part of that link equation is how big can I make my ground aperture, and we've already heard some discussion of some very large apertures that exist on the ground and are being considered for deep space links. I just show here as another example what was developed for that primary ground terminal for LLCD, where we had 8 telescopes that were mounted on a single gimbal. The downlink collector were these 4 16-inch telescopes, and the uplink transmitter was 4 6-inch telescopes. All of these telescopes were fiber coupled to amplifiers and detectors that existed in this shipping container. And they were enclosed in an air-conditioned dome that allowed us to maintain their pointing and allowed us to acquire very quickly during the mission. Everything that controlled the telescopes and the operators included resided in the 16-foot shipping container. It was designed to be transportable. We actually built this up at Lincoln Laboratory in Massachusetts. And then a couple months prior to the mission, we moved it out to White Sands, New Mexico for the link demonstration with LADI. And then the other key technology that exists here is the photon counting detectors. And so in this case, we used superconducting nanowire arrays. And these particular detectors were developed at MIT and Lincoln Laboratory. And they use a thin film niobium nitride nanowire that's patterned onto a surface. And the way this works is you cool this down to a cryogenic temperature. For these particular detectors, less than 4 degrees Kelvin. At that point, the wire becomes superconducting. And you image your received signal onto the detector, and a single photon that hits the wire interrupts the superconductivity of the wire for a short period. And so by passing a current through the wire, you can detect that change in superconductivity, and that tells you when a photon has been detected. These particular detectors are very efficient. In this case, we had greater than 70% detection efficiency. More than 70% of the photons that arrived were detected. They also have a fast reset time, less than 10 nanoseconds. And what that refers to is after a photon is detected, the wire is disabled for a period and then has to become superconducting again before you can detect the next photon. And so at 10 nanoseconds reset time, that means the fastest count rate that I can count is 100 megahertz. And I already told you we did the link at 600 megabits per second. And so the way you do that is that you have multiple detectors that you image your light onto. And so when one is disabled, the remaining detectors can remain active and detect the next photon with a little bit of loss. These detectors also have fairly low timing jitter. And so again, with pulse position modulation, what we're trying to measure is the time of arrival of the photon. And so if the detector has a lot of jitter, that ultimately limits how well you can determine which slot the photon arrived in. And so for these particular detectors, that was about 40 picoseconds. For LLCD, our slot frequency that we used was 5 gigahertz, so 200 picosecond slots. And therefore, this timing jitter was adequate for the system that we had. They're very low noise. In fact, the dark counts that you get from these detectors in operation is pretty much inconsequential compared to the other noise sources in the system. And by doing this, you can get better than 2 bits per detected photon in the ways that I just described to you. And here's just an example of some of the measured performance of this particular receiver. And so what this shows is in terms of power collected into our received fiber, what the code word error rate was for the system at the different data rates ranging from 40 megabits per second to 600 megabits per second. And here you can see how that maps to sensitivity in terms of photons per bit. At the lowest data rate is about 1.5 photons collected per bit. And at the highest data rate is about 3.4. And the reason that it degrades is because of that saturation effect, where at higher fluxes, the detectors are off more of the time because of the finite reset time associated with the detection process. So that's what I have to say. Again, operational near-Earth optical communications systems are a reality today, and the European Data Relay System is what's up there today. There are other systems being developed, like the Laser Communication Relay demonstration by NASA that will also be up there soon. And for deep space, you can get very high data volume delivery with optical comm, and there's been at least one example of that to date, and there are more on the way. The big issues that you have to deal with are how do I track the beams and point them, and how do I efficiently detect the signal that's collected at the ground. And so I've shown you some examples of how we've done that with prior systems, and I think there's a lot of promise here for future systems to really demonstrate the utility of this technology. So thank you for your attention.